Okay, move.
I'll show you some weather going on behind me. How's that?
That's perfect. Yeah. We like weather.
There we go.
Oh,
that way you can see, well, tons of paper getting ready. Star behind me, or is there too much glare? Is that
no, fine. Where are you located?
I'm on the west side of town at Putnam Elementary School.
Oh, okay.
And I'm at 79912 zip code.
Right by the house I grew up at, so I know exactly where you are. Well, I'm going to introduce myself. My name is Marissa, and I'm a meteorologist here at the National Weather Service in El Paso. Mr. Jason Laney is also a colleague here at the National Weather Service in El Paso, and he will actually be your teacher. He's going to, we call this affectionately how to teach teachers to teach the weather. So, and then Mr. Bryce will be in and out as his computer works this afternoon. I just wanted to let you know we have a website dedicated to all the topics that Mr. Laney or Jason's going to go over today. Quick 30 to 45 minute stint. At the end, if you have any questions, you have questions during the series of Jason talking and all the topics, just let us know. We can go over those. And also, Tim will email you all the PowerPoints so that you don't have to feel like you have to write everything down very quickly, and you can have all of that material. And we're always here 24 days, 7 days a week, and you can always email us. So without further ado, I'm going to share my screen, and I'm going to pass you over to our teacher, Jason Laney.
Very good. Well, don't feel bad about being a teacher here. We've done some other teacher trainings that have just been one-on-one, and they've gone really good. So issue for us whatsoever. Just to kind of give you a little background here, we started doing a similar presentation for students, 4th, 5th, 6th graders, and it was basically together based on some of the TEAC testing items the teachers needed to cover for the students to be able to take their test. And so it jumps around just a little bit, but we've tried to kind of homogenize it somewhat. And what we found that not only were we doing a good job teaching some of the students, but a lot of the teachers were learning some stuff along the way. And the teachers kind of wanted some one-on-one or two-on-one or three-on-one time with us so that they could possibly get a little better understanding of this. And I go through this. This is basically going to be the same slides that we give to the students, but I more or less kind of home the ideas of how we like to teach it for the students as well. Some ideas of some comparisons you may want to use to kind of draw some parallels as you're talking about these things. So with that said, we're going to move ahead, Miss Marissa. We call it Weather Basics, and of course there's a lot that goes on when it comes talking about the weather, but one of the things that we start out with the students, and the students kind of find this amazing, is we say that it all starts with the sun, because if it were not for the sun, there would be no weather. The sun is really the driving force behind it. So one of the things you have to think about, what would happen if we didn't have a sun, right? Well, obviously, if there's no sun, the Earth would just be a frozen mass. There would be no heat energy to kind of pass around, and obviously we wouldn't be living here. So the sun, as you might important when it comes to the heating aspect. But one of the other things that we kind of teach the students is while the sun is responsible for heating, believe it or not, the sun is not the force that heats the air. The sun doesn't heat the air. It turns out that the sun heats the earth, and then the sun turns and heats the air. And that's because when we talk about heat energy from the sun, we talk about this transmission as being a transmission. I'm not sure if you've ever gotten this deep into it with your there, but basically there are 3 forms of heat transfer. If you want to get heat from one point to another, you can do it through convection, and that takes place in our atmosphere. You can do it through conduction, and that not so much, a little bit, but not much, or through radiation. And radiation is defined as the measure of heat transfer through the vacuum of space. Obviously, we don't have a big metal rod from the sun to the earth, so we can't conduct the heat back that way. And there's no air to move, so we're not going to get any convective currents, no conduction. So the way that the sun's energy reaches the Earth is through what's known as radiation. And radiation is important because radiation comes in all wavelengths. Some of the radiation is a short wavelength, other radiation is a longer wavelength, but it turns out that the heat energy that comes from the sun primarily comes in what's known as short-wave radiation. And that's kind of important because the air that surrounds the Earth, now we don't go this deep when we're teaching students, by the way. This is really for your edification, and you can kind of as much as you want to with that. But it turns out that the air that surrounds the Earth is what we call a selective absorber. So what it does is it absorbs the doesn't absorb the shortwave radiation coming from the sun, so basically it's like a window. It passes straight through to the Earth, where the Earth lights up, and then the Earth gives that energy back as long-wave radiation. And that's what the atmosphere, remember I said the atmosphere was selective. It doesn't like the radiation from the sun, but it likes the radiation from the Earth. So we say the sun heats the Earth, but the Earth heats the air. Well, that would be kind of interesting if you think about it, but have you ever noticed that around the Earth that it's not the same temperature everywhere? The general consensus is the closer you get to the equator, the warmer it's going to get, and then as you go up towards the poles, whether it be in the northern hemisphere or the southern hemisphere, it's cooler. But we're all receiving the same amount of radiation from the sun, aren't we? Well, believe it or not, we're not. What is very important when it comes to incoming solar radiation in the Earth is the angle that it is received. And because the sun is so large in relationship to the Earth, if the sun's radiation is coming in parallel rays. But the Earth, as Christopher Columbus told everybody back years ago, the Earth isn't flat, it's nice and round. So it turns out that the rays that come over the equator are more vertical. They're more straight up and down. So that would be radiation that comes in straight like this. The more vertical the radiation, the more direct and the more intense it gets. You get up to the poles, the radiation kind of comes in at an angle. And there's several reasons why it's not as intense when it comes past through more atmosphere. So basically, remember, the higher the sun angle, meaning 90 degrees, that's the highest it can get at midday, the warmer it's going to be. So let's see if we can step forward, Miss Marissa, and we'll explain this little thing called that kind of explains away why it's always colder at the poles and why it's warmer at the equator, because the equator gets the most direct radiation. But then you have to get into this idea, well, okay, well, isn't the temperature the same year-round? Obviously, in wintertime it's colder, and in the summertime it gets warmer out there. And a lot of that has to do with the Earth's tilt on its axis. So if we're looking at, say, the first day of spring or the first day of fall, what happens is the sun is directly over the equator. And when I say equator, that means the most direct rays, the 90-degree angle that it's coming in. I guess I should do this, coming straight down like that. Through the seasons, the center of where the sun hits the Earth migrates north of summer and south to the Tropic of Capricorn, which is the first day of winter. So when we have these equinoxes here, notice that not only do we have equal amounts of day and darkness out there, we find that the sun angle is greatest at the equator, and of course it's lower as you go up. Now, let's go ahead and take a look at the first day of summer here, and notice that the Earth no longer is straight up and down on that axis, but that axis is tilted. And that to all of this. If the Earth were not tilted on its axis, we wouldn't have our seasons. And because it's tilted on its axis, that means at some point during the year, the sun's rays will be direct over not the equator, but over the Tropic of Cancer. By the way, the Tropic of Cancer, 3.5 degrees north latitude. And the reason why that is the tropic is because the Earth's tilt on its axis, 23.5 degrees. It kind of comes together. If we ever any geometry here, we can kind of put that together. You can even use this in math class if you like. So this is why the northern hemisphere is so much hotter in the summer. Look over to the north of the Tropic of Cancer. The sun angle 66.5 degrees. That's pretty high. That's higher than it is over the Tropic of Capricorn in the southern hemisphere. That's why the northern hemisphere is experiencing summer, while at the same time down in the southern hemisphere, it's winter time. Now let's fast forward 6 months and you're going to see just the opposite. Now the highest sun angle has migrated south of the equator and is over the Tropic of Capricorn. Meanwhile, up here close to where we are, you'll notice that the sun angles have gotten considerably lower out there. And not only are the sun angles lower in wintertime for the northern hemisphere, if you'll look north of the Tropic of Cancer, there's a lot more of that globe that's shaded in darkness than illuminated by the light. The days are going to be shorter because of the tilt on the axis. So that means there's less time for us to absorb radiation. Even at a low angle, if you get that low angle for long enough time, you can still accumulate a little bit of heat, but the days end up shorter, the sun angles are low, and it is much colder. So it's the Earth's tilt on its axis that's responsible for, but a lot of times when we teach this to students, the students, after seeing these images, they start thinking, okay, this is the axis of the Earth, right? Well, at summertime it wobbles this way, and then at wintertime it wobbles back this way, and then summertime, no, that's not what The Earth's tilt on its axis is constant. It never changes out there, which is the position of the Earth in relation to the sun. Because while the Earth itself is moving around on its axis, we call that rotation. That's responsible for day and night. It's also making its way on a 12-month journey all the way around the sun, and that's what we refer to as revolution. So the Earth has two primary motions: rotation on the axis, day and night, and that heats and cools, obviously, in 24-hour cycles. In the revolution, it revolves around the sun, and that's responsible for the seasonal changes. You see, even though the axis tilt didn't change, when it's on the left-hand side of the screen, that's summer. The northern hemisphere is tilted towards the sun, and by the time you get over to the right-hand side of the screen, six months later, or the first day of winter, the northern hemisphere has now tilted away. So this kind of explains what we call our differential heating. Let's go back to that first slide. Remember, I said if it weren't for the sun, we wouldn't have weather. Even though the sun doesn't heat the air, eventually the air gets warmed because the sun heats the Earth, and then the Earth heats the air. You've got a lot of differences in heating of the Earth. Differences in latitude. The further north, the further south from the equator, you're going to get lower sun angles. You're going to get less heat. You get, why is all heating important? Well, it's important because that's what drives pressure patterns. Now, even areas that have the very same sun angle, imagine that we're right here. Well, we're in El Paso. We don't have a lot of water nearby, but you have areas at the same latitude. There's somewhere west of here in California that's located at the same latitude as El Paso. Chances are they're not as warm as we are today. That's as well. Land gets hotter, and it gets hotter faster than water does. Now, the science behind this is manyfold. One, land can't move. It's stationary. Water can move, so it can start to get some currents going and some mixing. Obviously, that doesn't happen with the dirt. But a more important, again, this is going to be a little more advanced science, is something that we call the specific heat of water. Water requires much more heat energy to elevate to the same temperature as land does. So the specific plays in. But how we teach this to students so that we don't, is we tell the students, imagine you're at the beach, okay? You've taken your shoes off and you can't wait to go into the water. Across the land, remember, land gets hotter, faster, and to higher temperatures. As you're walking across that sand, sometimes that sand tends to burn your feet because land heats up faster and quicker. And so you're running as fast as you can across the land, right? Because your feet are burning. And the minute you hit the water, what happens? The water feels ice cold. Now keep in mind, they've received the same amount of solar energy. The land has, water has the same solar angle. They're right beside each other there. But that's a perfect example of how land gets hotter than water. So not only do you have changes in latitude, changes in the day, changes in the time of day, changes throughout the seasons, you have changes depending on whether we have land or water. So if we're here of the Earth, and remember that a good portion of the Earth is covered by water. There's a lot more water than there is land. So obviously you're going to have areas on the map, on the globe as a whole, that are going to get hotter than others. And there's ways to put it. Now there's a lot more to it than this, but a simple way to put it is when the air gets hot, the pressure gets lower. And we haven't talked about pressure yet, but we will in a minute. And when the air gets colder, remember, land is going to get hotter than water. So over land, notice I've positioned the L's. Those would be low pressures. And over the water, I've positioned the H's. Those would be high pressure. And that's all direct result of uneven heating. Uneven heating gives us even pressure. So why would uneven pressure even important? Because if you're like me, you walk outside one day and the weatherman says, hey, we have high pressure today. The next day the weatherman says, hey, we have low pressure today. Have you ever personally been important? Next slide will show us changes in pressure lead to movement of air. And moving air is something we've got outside in El Paso right now. Moving air we call wind. Always moves from high pressure to low pressure. So if you've got one side of your map or one side of the state and you've got low pressure on the other map, the air is going to move from the high to the low. And then moving air is what we wind. So believe it or not, the sun heats the earth, and that causes not only different pressures, but that causes the wind. So uneven heating of the earth can cause pressure and low pressure a little closer because they're responsible for so much more than just the wind. Notice in high pressure, I've got a nice sun up above it. And in low pressure, I've got that's a very good generalization. Normally, high pressure has nice weather. Low pressure has, well, not so nice weather. But as you take a look at high pressure, take a look at my arrows over the H. Notice that they're sinking. Air sinks, and as it sinks in high pressure, it hits the ground, and it hits the ground, and it spreads out. So the air actually moves away from high pressure. And in low pressure, it's just the opposite. And one thing when you're teaching water, opposites are going to be key because there are lots of opposites that go on here. Low pressure, the opposite of high pressure. Instead of the air sinking, the air rises. And instead of flowing away from high pressure, the air flows into low pressure. Makes sense because remember I said air moves from high to low pressure. So a closer look at high pressure right quick will kind of break down some of the teaching points that we like to give the students here. First of all, we represent high pressure with the letter H. Sure, it's the first letter in the word high, but it also stands for happy weather because high pressure usually brings clearing skies. You've got blue skies. Now, it might be a little cold, but if it's nice and sunny out there and the wind's not blowing too strong, it'll feel pretty good. So you end up with clear skies, calm conditions because the winds are the air is sinking, it's nice and dry, and you can, with sunshine, get nice warm temperature. It gets a little cold at night. Now, low pressure, remember, it's going to be the opposite. So instead of cold air, which is heavier and tends to sink, the map was areas over the land usually that were a little bit hotter. Well, hot air, the air rises. That's why people go for flights in hot air balloons, not cold air balloons. Cold air balloons would crash to rise because the warm air is more buoyant. Now, the L on a weather map, sure enough, is the first letter in the word low, but to relate it to the students, we say that it also means lousy because that's the kind of weather you're likely to get with low pressure. Because as that warm air is rising, you end up causing condensation. So moisture begins to pool above it. And you get, of course, get windy conditions. High pressure race car in a drag race, it starts at the beginning, and it takes a while to accelerate to top high pressure because that's the starting line. And it's fast once it reaches low pressure because this is the finish line that it's coming towards. And of course, you're not only going to get wet weather, and a lot of times this is going to be followed by some cold weather as well. And you'll see all this stuff on any weather map that you look at. Watch the guys on television tonight, tomorrow. Take a look at it in the USA Today or the Times. And on a weather map, you're going to see it all. You're going to see H's and L's, and you know that those H's and L's were created because of uneven heating. You may not have known that before today, but now you do. We'll blame the sun for that one. So areas of high pressure and low pressure. And we know that when you get differences in pressure, you're going to start getting wind that's going to start moving. Some areas are going to be clear. Some areas are going to be cloudy. Some areas are going to be cold. Some areas are going to be warmer. And oh, by the way, what happens when cold air and warm air are side by side? There's a dividing line between them. And you see that on our map as well. It's what we refer to as definition of front, is a boundary that separates air masses of different density. But when you start using the big words with fourth, you're going to lose them real quick, we found out. Lose teachers. But basically, cold air is more dense than warm air. So if you have an area like on this weather map where over West Texas it's cold and over Central and East Texas it's warm, there's a very sharp line that defines those two. And that's called a, by the way, there's some other types too that we won't really get into today. But what determines whether it's a warm front or a cold is which one is actively taking over the other. So if where I am it's warm and cold air is trying to take its place, if the cold air is the one on the move, it's going to be a cold front. However, if it's the warm air that's coming in to take over, then it's going to be a warm fronts and cold fronts. They look a little different in the cross section here, but basically cold fronts mean that cold air is coming and it's pushing warm air out of the way. Warm fronts mean that warm air is coming and it's pushing cold out of the way. But I did mention something about density earlier. I said that cold air is more dense. I relate cold air as to being, because it's bigger and more dense and stronger and more forceful, it can push warm air out of the way, and warm fronts can push cold air out of the way. So that means that cold fronts are going to move more rapidly. Warm fronts are going to move a little slow. It's on the side here. But if you watch the animation, as that air is lifted rapidly along the cold front, what happens? The cold front comes in like a wedge. So I've got moist and it's humid, and that warm air just slices right up that wedge there. And front moving so fast, it creates clouds that we call cumulus clouds, the puffy clouds that build into the sky. Typically, cold fronts are associated with stormy weather. Warm fronts are associated with cloudy, kind of gloomy weather. Most active type weather usually going to be caused by a cold front as it moves across, since we are broadcasting from Texas here today. Notice a cold front means it's the leading edge of colder air. Now the little triangles that you see point to the direction the cold air is moving. So this means the cold air is back in New Mexico. And you can see temperatures 70s and 80s across Texas and warm. Well, Tuesday comes and cold fronts move fast, and I know Texas is a big state, but look how fast that thing's already halfway across the state in just one day's time. Areas that have fallen behind that cold front have gotten colder because cold air is taking over by, and the front's cleared just about the entire state, and the entire state is cooled off. So cold fronts are going to affect our temperatures. Obviously, they're going to bring colder weather. She did our public forecast today, and she was telling me that we've got some of that on the way. A cold front's heading in right now. So let's step back in time. Let's go back to Monday, and this time instead of putting temperatures, let's put some weather images on the map. And notice in the warm air, maybe a few clouds but no rain, but remember the cold front lifts the air more rapidly. Cold fronts produce rainy, stormy weather, and sure enough, West Texas is getting the storms on Monday. By Tuesday, West Texas has started to clear out. Where are the storms? Right there on that front in the middle part of the state. And finally, by the time we get into Wednesday, those fronts have pushed eastward. And one of the things we notice in Texas is that the weather gets more violent the further east it goes because those cold fronts have more moisture to find. So moisture is going to be a big player in all that, to our next point that we talk about, and that is the idea of the water cycle. Now, anybody can teach the water cycle, and you can sing the little songs, you know, about, I don't remember the song, I'm sorry, you're probably glad you don't have to hear me sing there, but the key to the water cycle is this little phrase that I put on your screen. Water. It's the only substance that can exist naturally here on Earth in all three physical states of matter. When we talk about it, no, we're not talking about the states of New Mexico and Texas and Arizona. We're talking about the states of matter, solid, liquid, and gas. A lot of things that can be solid, like CO2. You can have solid, and we call that dry ice, but that doesn't exist naturally, especially controlled conditions. But water, on the other hand, good old H2O, it can be a solid, it can be liquid, it can be gas, and it doesn't need special laboratories to change. Its laboratory is the atmosphere around us. Water is the only substance that can do that. So when we talk about the water cycle, one of the things that we like to talk about is the change from one state of matter to the other. And some of the ones that are going to be very important to the... Now, evaporation comes from the oceans and from the lakes and the rivers, although most of the evaporation does come from the oceans because, let's face it, there's more water there. That's how we get water in the air. So change of state from liquid to gas. Now, what caused that to happen? Are you thinking right now with me, what would cause it to go from liquid water to a gas? Obviously, we had to heat it up. Where did the heat come from? It came from the sun heating the water and heating the earth. Again, the sun's responsible for weather, not just pressure and winds, but changes of air. That's how we put water in the air around us. And as that air continues to rise colder and colder with height, because the sun heats the earth heats the air. So the air close to the earth is going to be the hottest. The air up high in the sky away from the heat source of the earth going to get cold. That water vapor, that gas, begins to return to liquid water drops, and that's called condensation. So you hit evaporation by adding heat, condensation by taking heat away. And that is what really fuels this entire thing. Now, there's some other tations that we talk about. For instance, transpiration is to evaporation, but that's the way that plants provide water vapor to the air. I like to say that's the way plants sweat. plants transpire, people perspire, perspiration versus transpiration. And of course, when the water droplets they kind of, by the way, just so you can remember this, takes about 1 million cloud drops to make one rain. Lots of little droplets of water up there suspended in the air. And they're so tiny, it takes 1 million of them to make one raindrop. That explains why clouds can remain hanging out in the sky above us. So remember to changes of state from solid gas back to solid and back to liquid. By talk about solids in there, that can be important weather too, but really evaporation and condensation are going to be the big driving points when it comes to getting that. And of course, it only, as I said, molecule. So that kind of gets you through this whole idea of how the sun really is responsible for weather. Uneven heating, uneven pressure. That pressure, of course, creates all kind of things: rising air and sinking air and wind and moving air. And then, of course, that air may have to learn is this thing called hurricanes. I'm running a little long here, so I'm going to try to get through this right quick. Hurricanes are the greatest storm on Earth. Now, hurricanes are something we don't see a whole lot of here in El Paso, some of them, but they don't necessarily come our way. One of the things we talk about with hurricanes is where they get their name. They were actually named after a Caribbean god, a Caribbean storm god. Where hurricane actually comes. So for those of us living here in the northern hemisphere and in the United States, we call hurricanes nothing more than hurricanes, but really all a area of low pressure out there. So we're going to step ahead and look at them on the map, but different countries have different languages. All things different, obviously in hurricane, but that's pretty close to hurricane. You get over in the Indian Ocean, it becomes a cyclone, which a cyclone is that thing that carried Dorothy away in the Wizard, wasn't it? It was a little bit different, but the same name. In the Western Pacific, they're referred to as typhoons, and off the coast of Australia, they're called Willy Willies. And Willy Willy, that's real funny when the students get to hear that one, so you'll have a lot of fun teaching that. Different names, they're all the same thing. So what exactly is a hurricane? A hurricane is an area of low pressure. Remember, low pressure was caused by heat. Well, it's to be colder than the land, but hurricanes form over the oceans. Well, they don't form over the Arctic Ocean. They don't form over the Antarctic Ocean. They form over the tropical oceans. And only in the summertime, that's when the waters are going to the equator. They've got the highest sun angle. Hurricanes need ocean waters of a good 80 degrees Fahrenheit or higher to form, because that's going to create our low pressure. And remember, low pressure, as you can diagrammed here, you've got lots of evaporation over the oceans because of evaporate, and you get this water vapor, and it comes together and hits the low pressure. And low pressure, the air comes together and converges. So when air hits like this, it has no flow, but it can't go down because the water's blocking it. It can't pass through each other. So when the air converges, it's forced to go up and rise. Rising air. And when the air rises aloft, are pretty light. So these hurricanes, while they spin at great speeds, forward motion is usually pretty slow. So taking a look at the anatomy of a hurricane, there are a couple of things, a couple of terms that we want to point out to you. One is the center of the storm, known as the eye. The next is the band of storms that work around the eye. That's known as the eye wall. And finally, you have these bands, these spiral rain bands on the outside. Now, in the eye of a hurricane, the winds are usually light. The eye is the very center. I know low pressure, the air is supposed to be rising, but believe it or not, in the very center of a hurricane, the air actually sinks. And that's why you get an opening in the clouds. It kind of clears out. The problem is with an eye, even though the weather's not bad in the eye of a hurricane, obviously it's pretty calm there. The eye of the hurricane's only a few miles wide, maybe 10, 12 miles at most. And around the edge of it is where the most violent located. That's that wall of thunderstorms that surrounds the eye. That's why it's called an eye wall. It literally is a wall of storms. That's where the winds are strongest, the rain is heaviest, and you start getting these little walls of storms before the center ever reaches you. These are called the outward spiral rain bands. They can bring some pretty heavy rain too, and a lot of times tornadoes as they come land. And so you've got all of these, the eye, which is the center. That's where the pressure's the lowest, but the weather's the most calm. Basically, the anatomy of a hurricane. Now, one of the questions I always get from students is, why is it calm in the middle of a hurricane? And I always like to say, well, it's a little more advanced than the class we're teaching. day, but that's not good enough. When you've got an inquiring student who wants to know an answer, we need to give them an answer. So the answer is pretty simple. It's because of the size of the storm and the fact that the Earth is rotating. It's this little thing called the Coriolis force. Now, basically, what the Coriolis force says, I looked it up in a textbook, Coriolis force is an apparent deflection to the right of motion for a free-moving object in the northern hemisphere. That was a mouthful, wasn't it? Basically, the Coriolis force is the reason why air flows clockwise out of high pressure and counterclockwise low pressure. And if you tell students Coriolis force causes the air to flow counterclockwise into low pressure, they'll buy it. Good enough for them. We don't have to get into all the fancy definitions there. But because this storm is so big and so immense, as the air flows in counterclockwise, look at this left-hand side image. Notice the arrows where they come together. Are they coming together in the middle of the low pressure? No, they're actually kind of traffic jam right around the edge of low pressure. That's where that eye wall was. Currents are rising. So on the right-hand side there, I show the convergence, not in the middle of that low pressure, but along the edge, and that's what creates the eye wall, and that's why the winds are strongest in the eye wall and lightest right there in the middle. So the size of the storm and the Coriolis effect. The larger the object we're dealing with, the more pronounced Coriolis is going to be. Likewise, Coriolis is more influenced by wind speed. A very slow-moving wind is not going to be affected by Coriolis, and obviously hurricanes, they can have winds 100, 120, 130 miles. That is the idea behind hurricanes. And the final topic that we cover with students that are on the TEAC test is weather versus climate. And this is a tough one in this El Paso area because we have so many Spanish speakers. My wife is a native Spanish speaker, and I hear it all the time. It doesn't matter whether she's talking about climate or the weather. She uses words interchangeably. She'll ask me how the weather is outside. She'll say, ¿Cómo está tiempo? Or she'll say, how's the weather outside? The next day she'll say, el clima. And I'm like, do you want to know about the climate or do you want to know about the weather? I'll ask her that in English. She'll say, I want to know about the weather. I ask you about the weather. And I said, well, you know, basically, I like to put it this way. Weather is what is happening right here, right now. And climate is a sum total of all weather. So weather, right here, right now, and climate is the total of all the weather. For instance, example for that to teach students is, okay, look out the window. What time is it? Well, right now it's 10 minutes until 4. That's right now. Where are we? Oh, we're in El Paso, Texas. That's right here. So tell me what's happening. They'll say, oh, it's sunny. Okay, that's the weather. It's hot. Okay, that's the weather. It's windy. That's the weather. Weather is right here, right now. Whereas if we want to talk about the climate of El Paso, my mom may be coming for a visit in the middle of July, and she'll say, hey, how's El Paso in July? What's the weather going to be? I say, well, I can't tell you exactly the weather at any time and moment that far in advance, but I can tell you a generalization of what's going on. Generally in El Paso, it's hot, and in July, or not. I know we're a desert, but that's our monsoon season. We have moisture. Chances are we're going to get a few big thunderstorms in the afternoons, but at nighttime out there's going to be a cool breeze. You may even need a jacket at night, even though it's a little warm during the day. Notice that's a summation of the weather, time and place. We put it another way for you. Let's go ahead and take the weather side first, and oh, she took through it, so let's go ahead. This is good, Marissa. Weather is what happens at a particular time and place where climate can be generalized, even regional, and generally long-term. So tell your students this. Is it news? Because when you watch the news, they're telling you what's happening right here, right now. Or is it history? If it's news, chances are it's happening now, it's weather. If it's history, something that happened in the past, or what might happen because this is what always happens this time of the year, that would be climate. So we read it one way like this. Climate is what you expect. So my mom comes in July. She expects it to be hot and humid. She expects some afternoon thunderstorms, and she expects cool nights. Weather is what you get. Just because that's what you expect, she may get here, and it may not rain at all, may not be humid. The monsoon may disappoint us this year. Remember, climate is what you expect, but weather is what you're. So that's really what we talk about. We talk about high pressure and low pressure because that's important for TEAC testing. We talk about cold fronts and warm fronts and the fact that cold fronts produce the most vigorous weather. That's important for TEAC testing. Now, we do talk about the seasons, but we like to touch on, as we mentioned, the water cycle and the changes of state, as well as hurricanes. Even though we don't get hurricanes here, they're important in other parts of the country. And then finally, the difference between weather and climate. So in 37 minutes. I was supposed to do this in 30, but kind of put it simply for you, I used to teach a class at the community college level, and most students were teachers coming, getting their continuing education, wanting to learn how to teach weather. And I taught it in an entire semester. So for me to try to break this into 30 minutes, Tim did me a grave injustice, but hopefully you got that still with us. We picked another school, Miss Blanca's school along the way. You guys, and pass to Miss Marissa, and she may have something for you. And if you guys have any questions, I'm not in a hurry. You may be, but I'm good to go.
Yeah, if you guys have any questions, Miss Blanche, do you have any questions? We'll start with you. You can ask Jason. So, Miss Blanche, I think you might be muted.
No, she's good.
You can hear her?
Yes.
Oh, sorry, I can't hear you. Go ahead.
Mr. Tim, I didn't hear her either.
I can't hear her, Mr. Tim, so you'll have to answer.
I don't.
Well, we'll switch over and see if we got two students hanging out with Miss Bianca, and I remember that name. You've been along with some students along the way, haven't you?
Yes.
Very good, very good. Glad you guys could make it today.
Do you guys have any questions?
We're very interested, and we would like to know if you all can share that PowerPoint, so at a point we can share that with our students. It will be a great review for our students to see those images.
Yes, PowerPoints, Mr. Tim will get those to you. And we also have a website, which I dropped in the chat, that is dedicated to these topics, that have supplement material, such as activities your students can do, YouTube videos that talk directly about these topics to help you and your students further investigate them. So if you're a couple of days away from STARS, we can definitely get you these PowerPoint slides. And I think next month, Mr. Tim, we talked about doing student weather training or basics again. So if you guys want to join then with your students, we would love to have you again, of course.
Also, do you visit the school?
Schools. I'll let Mr. Tim answer that.
Yeah, we certainly do visit schools. You just need to contact me or Miss Marissa or Mr. Jason, and one of us or somebody else from the office will be happy to come out and talk to your students in person.
Yes.
Great. Will be the same kind of a lesson that we provide and everything?
Actually,
yeah, go ahead, Tim.
Well, when I come out, each of our meteorologists kind of teaches it in a different way. I teach a lot of kind of experiments, and we have fun, and we blow things up, and we laugh and have a fun time. So it's not necessarily teaching straight to what you guys would be teaching on the STAR or anything like that. That's what I've been leaving these trainings for. More of it is just to kind of get people interested or get the kids interested in and excited about science and weather in general.
Okay. Do you have a limit of students that you see, or it can be a large group of students?
No, I've done everything from one class to an entire school in a day. So
Okay.
whatever works for you guys.
If you guys don't have anything else, I don't think anything else. Good. Okay. Well, Miss Blanche and Miss Blanca, thank you so much for joining. Tim, Jason, thank you guys for your help today also. Okay, we're going to do some student segments later on towards the end of the school year. I guess school year's kind of wrapping up for you guys. And we have the website, and we'll get you those PowerPoint slides. So thank you for joining us. We really appreciate it. Have a good afternoon.
Thank you very much.
Bye-bye.